So I will be talking about different algorithms for the multi-users cases, right? And then I will also be talking about the hardware testnet which we had created for those algorithms. And then at the last part, I will be talking that how this multi-arm bandit and reinforcement learning algorithm can also be used in IoT networks, right? And then we will conclude the session with some open research problems, right? So what exactly this reinforcement learning? You can see that it is a subset of machine learning. So as Professor Raji was talking about, basically the machine learning has been divided into three major parts. Although he has in his own diagram, he had further shown this deep learning and then deep R learning. So that is further the subset of this machine learning, right? So machine learning has broadly been divided into three parts, including unsupervised learning, supervised learning, and reinforcement learning. So a very basic definition of reinforcement learning says that it is learning what to do, how to map situations to actions so as to maximize the numerical reward signal. The learner is not told which actions to take, but instead must discover which actions yield the most reward by trying them. It's a typical definition by Sachin and Bhatt, but I will explain this definition by taking one of the very basic examples through which you can easily correlate this definition to the example, right? So the very basic example is a small newly born baby, and if a newly born baby wants to learn how to walk, so initially he does not know how to walk, right? So you can say that the learner is not told which actions to take. So although the mother of the child tries to make him learn how to walk, but exactly she cannot tell. So what exactly? So what I can do that say that the learner is not told which actions to take, but instead must discover which actions yield the most reward. And what does this reward means? That what actually happens that the kid tries, falls down, again stands up, again falls down, again stands. So this process continues, and with this due process of falling and standing, he or she knows how to learn. So how can you correlate this definition? That but instead must discover which actions is the most reward by trying them. Means he is trying by falling and standing, and then he discovers that how I can exactly learn how to walk, right? So this is basically a very typical example of this reinforcement learning, and how this reinforcement learning works. So the goal of the reinforcement learning is to train an agent to complete a task within an unknown environment. So unknown environment because we don't have any idea about the environment. So basically this in more detail I will be showing you in next few slides that why do we say that we don't have any idea about the environment, and then how do we learn from the scratch, right? So the agent receives observations and the reward from the environment and sends actions to the environment. So if you remember, yesterday Dr. Sumit was talking about a game where one of the candidate was pulling like arm out of that, he was giving a reward, and based upon some exploration and exploitation, you have to finalize that which is the best one, right? So basically this agent takes two components, a policy and a learning algorithm. A policy is a mapping that selects actions based on the observations from the environment. So as I said, what is the policy of that child? That which actions, right, falling and standing actions based upon the observations he has to map and learn this, right? And then based upon that, the learning algorithm continuously updates the policy parameters, whereas the goal of that algorithm is to find an optimal policy that finally maximizes cumulative reward, or in turn, I can say, minimize the regret term, which yesterday he was talking about. So a very basic understanding of the multi-arm bandit framework can be done with the help of this example, this diagram. And this is typically a diagram of a casino where you say that 5 machines are put there. Now, A gambler goes to that casino, pulls let's say put a 1 rupee coin in that and gets 10 rupees. What about the second time? So let's say he has to take attempts. So that game is similarly what Dr. Sumit was talking about yesterday. So if I get 10 rupees in return, I don't know how much other machines are going to give me back. So I must explore other machines as well. Then only at the last of that, we will be able to decide which is the best machine, and based upon that, we will be selecting the best machine, which is, so initially we need to explore all the machines, and later on, once we have a clear idea of that, we will be uh, exploiting that machine. We will be exploiting that machine, right? So then, uh, let's come to the multi-armband framework. So exactly this is what the gambler is to maximize the collect rewards, some through iterative pulls, and we have to maintain the exploration and exploitation trade-off, right? So now coming to the basically cognitive radio networks. So yesterday was what he had given us a hint that what cognitive radio says about that there are two types of users. There are primary users and secondary users. And primary users have the license to use the spectrum, whereas the secondary users, or we also say cognitive radio users, have to access that spectrum intelligently. Means they don't have the license to use that. So now with this diagram, what we can see that the in yellow color, they are the licensed user, whereas some part of the band, a frequency band or a spectrum, you can say that they are being occupied by the secondary users because they are not being used by the primary users, right? So this is how this whole networks works, that there is a base station. Right. So what exactly in each time slot it happens that initially we select a band or say channel, then do for some time it needs some sensing, and then we do the transmission, and at the last of it we get feedback, right? Which kind of feedback? So we will quickly come to the point of collision, and then you will understand. So now what this slide says that then what is the role of reinforcement learning in this? So basically, since as I said, primary user have the access of the spectrum and secondary users don't have, so secondary user have to exploit the unoccupied band, and unoccupied means which is not occupied by the primary user. And in that case, firstly we need to learn the spectrum of occupancy probability. So this learning is being done using the reinforcement learning algorithms, right? So now directly coming to the multi-user case and the motivation of the research, right? So as yesterday we had discussed that when there are multiple single user case, he has already discussed. When there are multiple users, then there is a high probability that if more than one secondary user tries to access the same channel or same spectrum, in that case, there may be a collision. And in that case, none of the users will be able to access the spectrum. So the challenge is that we have to design our algorithm in such a manner that the number of collisions among the secondary users should be as minimum as possible, because the collision leads to inefficient use of battery, power, spectrum, and time. Because if you have not successfully transmitted your data, in that case, you have to resend again and again, right? So goal number one is that we have to minimize the number of secondary user collisions. Then what about second challenge? That we practically, we don't know that how many users other than me are trying to access the same channel which I am, then in that case, what will happen? Since I don't know, I will try my own learning, others will try their own learning, and finally, we have to save ourselves with the collisions. So, the first another challenge is that how will you know or how will you estimate the number of the secondary users other than you in the network, so that it will be easier for you to design your algorithm in such a manner that finally you can avoid the collision. And then final goal of the algorithm will be to maximize the throughput of the network. So the objective, which now I am going to discuss about the few of the algorithms. So objective of the algorithm is that we should design our algorithm in such a manner that it should have higher spectrum utilization with minimum number of collisions. And then once we design such algorithm, we have to validate such algorithm in the real time scenario on the hardware test bed, which is USRP, Universal Software Radio Peripheral based test bed, for which we have to verify in the real radio environment. And in addition, that we must perform the theoretical analysis, because you may agree with me, I hope, that once you are designing any algorithm, just simulating that in any on any platform such as MATLAB or Python or anyone, it does not make a lot of sense, and it cannot never be converted to a good publication unless and until you don't do theoretical analysis, as well as you have to validate it in the real time radio environment, right, using some prototype test bed. So this is what I have tried to include all these three parts in my work. So this is the network model we have taken, that initially we have U secondary users and N channels. Then this is time slotted communication is used, means initially there will be a primary user sensing, means we will sense that is there any primary user or not. If I find that there is a primary user, obviously I cannot transmit on that channel, because they are the licensed users and they have to they have all the rights to access the data on that. So if there is no primary user, if I don't sense any primary user initially, then I can transmit on the data, transmit my data in the remaining time. That is now, and there is always 0 or 1 probability in the IID distribution model of vacancy of a channel, means either it will be occupied or not occupied. There are only 2 possibilities, right? So this is what we have to do. So for that, now the first algorithm I am going to talk about. So basically we have divided the algorithm in 3 parts. That is proposed secondary user coordination with fairness algorithm. So what we talk about, that we have 3 goals while designing such algorithm. Number 1, that we don't have any idea about the channel statistics, that which channel is good, which channel is bad, similar to the multi-arm bandit problem in the gambling machine, that we don't have the idea of the characteristics of the machine, which is the best or which is the poor machine. In that case, firstly, we need to characterize or get the correct estimate of the statistics of the machine. Similarly, here we are going to get the correct estimation of the channel about their vacancy statistics. Once we are aware that what is the characteristics of the channel, then my next goal is going to be the number of secondary user estimation, because as I said, that we don't have any idea about the number of users other than me in the networks. So in the second phase, we are going to estimate the number of secondary users. And the third, once we are done with this, we are aware of the channel statistics as well as the number of users. Then in the third part, we will be exploiting it, right? So this is orthogonal and block hopping phase, where we are going to exploit the channel. So what exactly the CC, that is channel character, means how do we characterize the channel? right? How we characterize the statistics of the channel. So basically, it's a very simple. It may look very simple to you at this stage since I have done, but initially it was challenging that how will you know the estimates, right? So for that we had um, used two sequence, that is random hopping and sequential hopping. So as this diagram indicates that initially in the 4 time slots you can see that if there are 4 users, secondary user 1, 2, 3, 4, so they are just randomly selecting some channel. If they found it free, as you can see in the first time slot only, secondary user has 2. Secondary user 2 has selected channel 3 and he found it free. Green color indicates free. So they can immediately start the sequential hopping. So means what does sequential hopping means? 3, 4, 1, 2, 2, 1, 3, 4 like that. And there is certain logic why we had selected the sequential hopping that I will tell you just now. And if there is collision, what you can see in the first time slot only, secondary user 1, 3, and 4, since they were selecting randomly, all 3 of them had selected second channel. So that is why now they will select once again, and it will go like that. And at the end of 5th time slot, you can see that all the 4 users are on the different channels, that is 2, 3, 4, 1. And thereafter, all of them can particularly start sequential hopping. And what the funda of the sequential hopping says is that if we have sequential hopping, so final goal is to estimate the channel statistics. So what we want that, okay, let's say I'm trying to estimate the statistics of a channel. So let's say I select that channel 100 times, just similar to the machine problem. So if I'm selecting a machine 100 times, and out of that 80 times I'm getting a reward 1, means I'm getting 1 rupees coin in return, means the availability of that channel or capability of the channel is like 80 upon 100, that is 0.8. So that is what we are going to do. And why are we going to do it sequentially? Because if I don't do it sequentially, then there will be collision, and we are trying to avoid the collision. So that is why you can see 5th time slot onward, there is no collision among the secondary users at all. So this ratio, that is, you can see at the last line, that mu n bar is equal to Vn upon Sn. Sn is how many times you have selected a channel, and Vn is out of that how many times that channel is found free, right? So this whole complete ratio gives you the statistics of the channel. So now obviously here the theoretical analysis requires that how much time you are going to do the random sequence hopping, and then how much time you are going to take the sequential hopping. So this is how we have derived through the theoretical analysis, that after this much time slots, we can have the correct estimation of the channel statistics. Now, once you are aware of the channel statistics, then what about the estimation of number of secondary users? So in that case, you can easily look at that in this diagram. How do we estimate that one at a time? So there are 4 secondary users. Secondary user 1 is initially on the top channel, 1 channel only. You can see 1 to 7 time slot, 1 to 8 time slot, they are always on 1. So they will be constantly staying over there only. And what other secondary users will do, that they will be sequentially hopping as they were doing it earlier. Then what will happen, that secondary user 1 who is on that channel permanently for 8 time slots, they will just be sensing. And you can see here that in the first time slot, secondary user 2 has come across. In this time slot, secondary user 4 has come across. Secondary user 3 has come across. So what is going to happen, that each time he will be sensing there is some movement by some other secondary user. So just by sensing that movement of other secondary user on that particular channel, he will be able to estimate that, okay, this is the number of secondary users other than me in the network, right? So this is how they are going to. So similarly, every user will be on channel 1 at some time, and they will be estimating the number of secondary users. So again, the theoretical analysis, that obviously how much time you will be doing this, how much total time it will take, so that all the secondary users will have the correct estimation of the number of secondary users. So these are being given by the TNOHS and TOHS like these parameters, right? Then the SCF analysis part. So as two of the important parameters which we include over here is regret and the collision. So you can see here that we have derived that the expected regret of the algorithm, what will be. So this will be the expected regret of the algorithm. And then what about the expected number of collision? So this is the expected number of collision we are going to have, right? So this is how we are going to calculate it. Then another algorithm to solve the same problem, but with some changes. Right now, what I have shown you that after channel characterization phase, we went for this OHS phase, one hot sensing phase, to estimate the correct number of users. But in this algorithm, what we say, no, we don't need to go for separate OHS phase like thing. Rather than without estimating the channel statistics separately, without estimating the number of secondary users separately, we can directly go for tracking phase, and finally we can lock, means all the secondary users can lock themselves in one of the top channels without the need of any estimation. Because final goal is that every user should access one of the best channels, and that will be achieved by using the tracking phase with this example. So you can see that at the start of the second tracking phase, that is just after the end of the channel characterization phase, all the 4 users are on different channels. SU1, SU2, SU3 and SU4 are on different channels. But after certain time, why we have named it tracking? Because what will happen if this is secondary user 2, and what will it do, that it will just keep tracking upward. Tracking means just we will be doing the tracking upward. And what will it do? That okay, it will sense for some time to this channel, and it will found, oh, it's free. Then it will track upwards. After a certain time, again it will track this channel and see the okay, this is free one. Okay, so again this will track upward. So now you can see after 19 time slots, these 2 users have moved upward. Similarly, after 156 time slots, all the secondary users will settle in one of the top channels, and which is the goal of the algorithm. Whereas we have not used any specific phase for designing for estimating the number of secondary users. So without estimating the number of secondary users, we have tracked upward in one of the top channels. This is the similar algorithm example, but this is the worst case example. We have shown that in the channel, at the end of channel characterization phase, all the secondary users will be in one of the worst channels. These are the 4 worst channels, and from here they have to track towards the 4 best channels. So this is the time they will be taking, and just by using this tracking algorithm, they will settle down in one of the best channels. So this is how the tracking algorithm works. So similar to the one hot sensing algorithm, again here also we derive this time, like how much time it will take to track upwards in one of the top channels. So that is given by TTR, that is time tracking time. And then similarly, all other parameters such as number of here we have seen that in how many times slot all the secondary user will confirm that okay, there is no secondary user in my next top channel. Next top. So next top means when this secondary user, or rather than understand with this example, that if this secondary user 2 is here, after how much time it will get assured that okay, this channel is free and there is no secondary user on that. So this is the time taken by NJ. So that in this much time slot, he will be confirming that okay, there is no other user in that channel. So at the last then we have calculated the regret and the number of secondary user collisions. Right. So these are the two basic algorithms, theoretical analysis we have done for the algorithm. Going for some results part, that you can see the we had compared our results with some of the existing state of the art algorithm, where this you can say MC top M was the one of the best algorithm at that time. And then there are some MC algorithm, SCF, TSN algorithm, all these are algorithm. Black one is my, this is TSN algorithm. So you can see here in this case that black is doing better than all the algorithms other than this red one. And there is a very valid reason why this fifth red one is doing good. That because in that algorithm it says that okay, we already know that what is the number of secondary users in the network. So now you can say that you have already given such an information to them which is practically not available. So in that case, obviously that will perform better. This is another where we have calculated regret. So this is the regret analysis and the throughput analysis. So you can again see that this black one, the throughput analysis means throughput of the network is at par with all the existing algorithms, right? This is one of the case which I didn't go in the detail, but let me tell you what exactly this is. This TDN, so TSN was for a static network, but this result talks about the TDN algorithm, means dynamic network. So what till the algorithm in OHS and TSN algorithm, what we have discussed, we have assumed that all the secondary users are static in the network. When we say static in the networks, means that once they have entered the network, they will be there throughout the network. But again, it's not a very good idea. It's not a very practical one, because you don't have any, you cannot have any control over the secondary users. If they have something to, some data to transmit, yes, they will be there. Otherwise, they will not be available in the network, right? So in that case, what will happen? So this dynamic network deal with that anytime users can come into the network, anytime he can leave the network, and best still we have to estimate the number of secondary users, statistics, and like everything, right? So for that we have done this and compared our results with all other algorithm, and we have shown that this is the black one in our one. Regret is minimum among all other existing algorithms, right? So now coming to the more important part, which yesterday Dr. Sumit was discussing about, that we don't do just the simulation, rather than we develop a prototype and validate on the proposed test bed. So this is the test bed, something looks like that. There are two USRPs, that is Universal Software Radio Peripherals. That is from ATOS Research, X310 board they are. So there are two USRP boards, and one laptop is being used as a transmitter and other one is as receiver. And so in this part, we have created our traffic generator at the transmitter side using the LabVIEW, whereas in the receiver side, we have designed our algorithm using the Simulink, right? So here you can get the details that left part consists of the primary user traffic generator and right part consists of the algorithm which we have developed. So primary user, in this diagram, I have shown you that it is being shown using LabVIEW. We had another version of it where we have created this transmitter using the GNU radio, right? So the traffic generator can be generated in the either GRC, that is GNU Radio Companion, or LabVIEW, whereas the hardware platform comprises of the X3 board, and these are some board details, right? Now, just I will give you a brief idea about this LabVIEW based transmitter what we have designed, right? So these are like multiband signal is generated by combining a set of subcarriers or FDM channels. So I think I was disconnected. So am I audible, Dr. Taran?
Yes, sir, audible, audible.
Okay, right. So yes, we have created 8 subbands over here, right? So you can see that we have divided into 8 parts, and each subband, and for that we have used one guard band between the two bands, and there is initially a synchronization band, synchronizing band to a start to show the start of the transmission, right? So, and this is the lab diagram, final LabVIEW based transmitter. So here you can see P underscore one, P underscore two, three, four. So these are the all 8 sub bands where we have created the traffic. And this is some output. You can see that this is here we have shown that 0.1, 0.2, 0.3. These are the characteristics or statistics of the channel they have learned with the time using the algorithm, right? This is a Simulink based receiver side. So here you can see that yesterday Sumit was talking about this several KLUCB, Bayesian UCB algorithm. So basically we have inside this Simulink block, we have created our own blocks for all these algorithms. And finally, this is the output block I have shown you, that where we have shown the number of transmission and all other parameters. Here, this successful transmission is percentage. Here, the number of collisions. So similarly, everything is shown using this Simulink model. So then, yes, this is another subset of the diagram, right? So how does it look like? Where you can see, just for your clarification, I have shown you that this is basically Simulink based from the MATLAB, where we have created this all the development. And just it's not that difficult, so you can easily do it, right? Now, in next 10 minutes, I will be talking about this reinforcement learning in IoT, right? And then bind up for last 10 minutes for some question answer if you have before going for the next session, right? So till now, what we have understood that what exactly this multi-arm bandits talk about and how it can be used for the cognitive radio networks. Now, what about IoT networks? Can it be used in the similar fashion for the IoT networks? This is another set of problem we have. For that, you can see with this diagram I have tried, and this is one of the most recent problem which my PhD and BTech students are working on. That and basically we have already developed this algorithm for this, but right now they are working on the hardware testbed creation. So testbed is already almost created. We are just trying to validate our created algorithm on that testbed, and thereafter like that will be converted to a good publication, I believe. So in this network, what exactly we can see that there is a gateway, and then you can see that there are different IoT devices. How the IoT devices works, that there are some IoT networks which use same IoT standard, and obviously because of this there will be some interference among them. And there are other type of networks, IoT networks, which use another IoT standard, but still they create interference in the same band. So what kind of research problem here we talk about? So here basically, now I will just try to correlate such IoT settings with the cognitive radio settings. So there, if you remember, we had talked about that how will you know that how many secondary users are there? Here again, the problem is how many IoT devices are there? And specifically, in such a scenario, IoT networks, the number of devices are going to be a much higher. So how to deal with such? Can we deal it with using the multi-arm bandits? Right. Similarly, the channel characteristics issue. You don't know. So here I have shown you the networks using different standards. So what about the channels in which IoT device is trying to transmit? What about the channel statistics then again the problem is how that IoT devices will know which is the best channel for me to transmit. Right. And let me tell you very clearly, not only the IoT network. So nowadays there is another type of networks which is a very highly demanded area of research, that is called reconfigurable intelligent surfaces, that is called RIS. So there also the problem is that how will you know that which is the best channel through which you can transmit and the reception will be the best. So again, such multi-arm bandit setup can be used there as well. So my main agenda was like that, to make you aware of the reinforcement learning and multi-arm bandit setup, which can be used for different applications, where I have given you the detailed idea of the cognitive radio networks. Here I'm giving you a brief idea of IoT networks. Other than that also, let me tell you about another problem which today Professor Rajiv Shaurya was talking about. So when he said that he has some nodes, right? So again, what I said, that how will you know how many nodes are there, right? Another problem, he said that there will be malicious users. How will you know that how many, let's say there are 10 users, how many malicious users are there and how many normal users are there? So such although since he was not, I think, very much aware of this multi-arm bandit setup, otherwise there is a direct solution to those problems that I have asked him. That yes, it can directly be dealt with the multi-arm bandit setup. In fact, one of my problem I have already dealt, where we have tried to segregate or differentiate what you say the normal users and the malicious users. So we had told that malicious users are jammers, that the purpose of the jammers will be to jam the signal, whereas the normal users will try to transmit the channel. So how to stop that fight and get your best possible throughput. So that was the goal in that, right? So here in this diagram, you can see that for such setup, we have for IoT networks, we had tried to compare it, and then you can see the UCD, which yesterday he was talking about, that is the simplest algorithm, and then TS is the Thompson sampling algorithm, and uniform is just a random selection, right? So random selection will always be usually the poor one. So that is what you can see from here. Whereas the Thompson sampling is the best one, but the challenge is the hardware implementation of that, which is a challenging task. So that is why it's not easy to implement the hardware part of this Thompson sampling, right? So basically, what I can say, that learning is here used to improve both the IoT network capability to support a large number of objects, because as I said, the number of object IoT devices will be as very high in case IoT network. So that is why how to support those large number of objects, as well as the autonomy of the IoT devices. And intelligence objects can improve their access to the network by using low complexity and decentralized algorithms such as UCD and Thompson sampling. So in next 3-4 minutes, I will bind it up. So I will come to the conclusion part, that in such work, we have tried to develop some algorithm for opportunistic spectrum access in the cognitive radio as well as the IoT networks, right? And then for its implementation, obviously, we had used the MATLAB toolboxes, right? And we have, in addition to the theoretical analysis of those algorithms, we have proposed the hardware test bed, which and validated all the proposed algorithm in the real radio environment using simulation, right? So in last 2 minutes, I will be talking about some open research problems using RL in IoT, as well as I will be giving you a brief idea about the cognitive radio networks research, open research problems as well. So let me talk about the first, the what you say, cognitive radio networks. So here I have discussed about two set of problems. First one is a static, where we assume that number of secondary users who have entered into the network will be constant, means they will be there throughout in the network. But later on, had converted that problem into a dynamic problem, where we said that okay, it's not mandatory that all the users will be there in the network, they can leave anytime. So we have already dealt with that. But another set of problem are channel conditions may not be stable. Channel conditions. So right now we have learned some other channel statistics, but it is highly possible that after some time those channel statistics itself will change. Then what will you do? Your learning done so far is not going to be useful. So in that case, you have to do a fresh learning. So how to deal with? How frequently channel statistics can change, and still you can manage your learning. So that is a challenging task, right? And which is again the practical problem, because channel statistics is something which is beyond your control. So you have to deal with it. Another is about the heterogeneous users channels. Means for one secondary users, a channel may be free, and another for another user it may not be free. Then what will you do in that case? How to deal with that heterogeneous channel? So these are some open research problems, and we have a lot of still a lot of scope, and my several students are already still working on that problem. About the IoT networks, you can see that to the work in the distributed and multiplayer setup. So still this IoT in the networks, very few work have been done for the multi-user cases, because again, this hardware implementation has still been challenging for us. So the hardware test bed we have developed so far is for just single user. So now we have to go for the multiplayer setup. So that is what we are doing. So for that, we have to create a algorithm and then validate it on that hardware test bed. And then there are several other scenarios which can be explored, like that what will happen if there is a joint correlation between the channels for those IoT devices. Similarly, what will happen if the time variation in the channel conditions, similar to the cognitive radio networks, right? Another, when all nodes, all IoT nodes don't have data to send at the same time, that is may not be competing, all be competing with each other always, because it's not compulsory that all the IoT devices will have something to transmit all the time. Then one will happen. And the last problem which I have written specifically, that is analysis with Thompson sampling, because as I earlier said that although simulation which I have shown you just now, everyone has explored that yes, it performs far better than the UCB algorithm, but none of the existing researchers have been able to do a very good theoretical analysis of the Thompson sampling, and that is the reason that still people are not going for the use of Thompson sampling, rather than they are being stuck to the UCB algorithm. And so the two challenges with the Thompson sampling is first the theoretical analysis, and thereafter another challenge is the hardware test validation, right? So these are the two different challenges we are having with the Thompson sampling, right? So with this, I think just in 1 minute I will summarize that in today's talk, what I have tried that I can give you a brief idea about the multi-arm bandit setup, about the reinforcement learning setup, and how such reinforcement learning algorithm can be used for this. Yes, what you say, some Abhiranjan is writing about the Thompson sampling algorithm. So I think I don't know whether you are just looking for, maybe I will take just question answer session, and then you can ask me directly what exactly you want to know about that. So basically, I have tried to show you the exact use of such how reinforcement learning can be used for the cognitive radio setup and the IoT setup. And I have given you just a brief idea that yes, it can also be used for the reconfigurable intelligent surfaces setup, right? So with this, I will stop my presentation over here, and I will suggest you that just feel free to contact through email at any time about me on my email ID. And now I will just stop sharing my slides and request you to ask me any questions if you have, right? So please. Abhiranjan is asking what is award and what is penalty. So award is very simple, that whenever you are selecting a channel, right? So in return, just similar to the machine in the gambling scenario, that whenever you will putting a 1 rupees coin, in return you will get something. So that is your reward, right? So similarly, when I am selecting a channel, if my transmission is successful, I will get a reward 1. If transmission is unsuccessful, I will get a reward 0. So this is the reward. And penalty is that if there is not a successful transmission, so it is the wastage of battery, right? Because I will have to retry my transmission. So this is the penalty. And finally, that is called a regret, right? So basically, reward which you get after the successful transmission, and regret what you get if you don't have the successful transmission, or if there is any collision. So this is what about penalty and reward. Yeah. So anything else you would like to ask me? Just I will more than happy to answer your query, please. So I will wait for a minute. If you have any query, then fine. And otherwise, we will directly go for the next session, which Dr. Sachin Taran has. So if you don't have any problem, means query at this stage, no problem. As I said, just feel free to contact me anytime through my email ID for any such research problem. If you are, some of you are new PhD students and who are looking for a good research problems to work on this field, if you are interested, just you can contact me. There are a lot of problems, honestly, open research problems to work on. So you can contact me anytime for that. And if already someone is working in this field, so feel free, we can have some good discussion, and if possible, we can have some collaboration as well. Right. Okay, so if there is no query, I will stop over here right now. Yeah, someone wants to say something? Okay, I think Dr. Sachin is there. Okay, so okay, I will stop now over here only, and Dr. Sachin, I will just request you to start up with session. So let's,
Yes, yes. First
yes,
of
so
all,
let's,
thank you, Dr. Rohit, sharing your wide research experience with all
mhm,
of us. And I hope everyone will be beneficial from your session. Thank you.
right.
Thank you.
So now I will just request Dr. Sachin to start with his session,
Yes,
and
yes, yes.
let's welcome Dr. Sachin. Yeah, thank you.
Thank you.
Over to
Thank
you.
you.
Thank you.
Dr. Rohit, my slides are visible.
Yes, it is visible. Yes.
Okay. Okay. Thank you. So, good afternoon to all of you. My topic is the adaptive signal processing for non-stationary signal and analysis and classification. This is the outline of presentation. First of all, I will give the basic introduction about the basic categories of signals and what kind of methods are generally used for those signals. And then what is the motivation for adaptive signal processing. Then we will come to the my proposed decomposition, that is the adaptive Hermit decomposition, and the result related with that, and then conclusion and future direction, and finally question answer session. So first of all, we all knows the basic definition of signal. Signal is basically conveys some information about some physical phenomena. Now, the information or nature of information will depends on that phenomena. If that phenomena is stationary, then we will get the stationary signal. And if that phenomena is some kind of random or regularly changing, then we will get the non-stationary. Like for a function generator. In case of generator, suppose we want to generate a signal, so we just give some input for the function generator, like we want to generate a sine wave of 50 hertz with amplitude of in range of +5 to -5, having some duty cycles 40% or 50%. And These all specifications are predefined. Once you have given this input to the function generator, then that function generator will generate the signal according to your specification. So if you see that signal on the CRO, then you will find it will never change in the entire duration of that signal. It will remain as it is. The frequency in each, suppose the signal is of around some 5 second or 10 second. If it is showing frequency of 50 hertz in a second, from in a duration from 0 to 2 second, then in 2 to 3 second or 4 to 5 second will also show the 50 hertz. So the aesthetics like frequency and other statistical properties are not changing with respect to the time. So we will say that this is a stationary signal, and its behavior is not changing, its frequency is constant, and its spectral content is also fixed. So but if that phenomena right now, using function generator, you given the fixed command, but if that phenomena is random, suppose if you are using multiple function generator, they are generating different frequency, 50 hertz, 20 hertz, and 30 hertz, and the duration will also changing, the duration is also changing. In that condition, the signal frequency content will vary with respect to the time. And this is the case of all practical phenomena or all physical signals. The situation is like this. Suppose if you talk about the brain signal, so whatever you think, at each instant there is a different activity inside your brain. Even same with heart also, you are getting some different kind of heart variation. Of course there is a repetition of PQRS, but inside that repetition of PQRS you will see the different variation, and because of that we are able to identify different heart diseases. Even same with muscles. Even if you are moving your arm in similar way in each time, then still the force for expansion or contraction of muscles will be different. Yeah, same with speech signal, vocal cord. If I say the like my name is Sachin Taran, so each time there is a different pulmonic air stream will be generated from my lungs. So because of that, that vocal cord or articulators will generate different speech signals. Even I say the same information, I'm again saying the my name is Sachin Taran, my name is Sachin Taran, but the lungs, that is the reservoir of air, will store different amount of air in each attempt. There is a different amount of air or pulmonic air stream is coming through the mouth. That's why the articulator is also act differently. Articulator, tongue, upper ridge, lower ridge. So same with fault signal also. Even same fault is happen with some machinery, but the intensity of variation will be different. Same with vibrations and earthquake also. So these are some kind of random phenomena which are not defined. In each time we will get the different variations. So if these are the random phenomena, then we cannot expect some kind of stationary behavior or stationary signal. So we will get the not stationary, or better to say the non-stationary signals. So how will you confirm that we are getting the non-stationary signal? Simple. Their frequency content is regularly changing with respect to the time. If suppose if your signal having the duration of 20 seconds, in 0 to 5 second you will see some different frequency, in next 2 second you will see the different frequency. So in each duration, or we can say the spectral content is continuously changing with respect to the time. Or even in some statistical person, they will say that we have a non-stationary time series. Non-stationary time series, that means their statistical properties are continuously changing. They have a different mean in different reason, different time interval, different standard deviation, different interquartile range, different mean absolute deviation. So their statistical properties are changing with respect to their durations. So sometimes they also call non-stationary time series as a non-homogeneous and homogeneous. And what is a homogeneous time series? Their statistical properties remain same. That is the homogeneous time series. And non-homogeneous time series, there are statistical properties. So not to be confused with a time series or simple one-dimensional signal or time-dependent signals. So some general examples of non-stationary signals: electroencephalogram, that is a brain signal, or we also called it EEG signal; electrocardiogram signal, ECG signal, it is basically a heart signal; and electromyogram signal, it is basically a muscle signal or EMG signal; and then fault signal is speech signal, a seismic signal. So you will find in our surrounding, the most of the physical signals are non-stationary. So because they are generated through a random phenomena or random behavior, so that's why they are non-stationary. So in signal processing, there are different methods. Dr. Rohit, am I audible? Okay,
Yeah,
okay,
yes, yes,
okay,
you are audible. Yes.
okay, okay. So in signal processing, there are different methods for analyzing these signals. From the basic one, first of all, discuss some station. You already know this, like a Fourier series or Fourier transform, short time Fourier transform, and wavelet transform. These all signal processing methods are defined with respect to the basis function. As you know, in case of Fourier series, the basis function simply sine and cosine. Why we opt that basis function? And in each method, whether it is a simple Fourier series or any complex technique like flexible analytic wavelet transform, whatever basis you are selecting, basis function or basis signals, basis, that means you are going to represent your signal in terms of those basis functions or basis signals. So the fundamental constraint for the basis function, they should form the orthogonal set. If you want to represent any signal in terms of those basis function, so your basis function should be orthogonal, like simple in Fourier series, like sine and cosine. If you multiply them, if you see their dot product, it will be zero. This is the simple definition of orthogonal signal. So that's why we opt the sine and cosine for representation of a periodic signal in a trigonometric Fourier series. So same with Fourier transform, we use the basis function like e to the power minus j omega t. The simple formula like f of t, and we will multiply by e to the power minus j omega t. But in case of Fourier series or Fourier transform, whatever basis you are using, that will remain fixed. अगर आपने एक बार मल्टीप्लाई कर दिया हुआ e to the power minus j omega t से, तो वो फिक्स रहेगा. You are just multiplying with a basis having a fixed frequency, that is a omega. But that is not the case with your physical signal. So you cannot model your non-stationary signal with some kind of stationary basis. Okay, so because your basis is not keep changing, it will remain, it will show the constant frequency. So you will get the huge reconstruction error for representation of that non-stationary signal. So in the beginning, people try to represent non-stationary signal using Fourier transform. So they got a huge error, a huge reconstruction error, because that basis inside the Fourier transform is not changing. It remains fixed, that is e to the power minus j omega t. Then people start thinking why we should not use the short time Fourier transform. Okay, your you need a basis for a short duration, and so why we cannot divide that entire duration of signal in a very small chunks or frames or short duration. So STFT is again the Fourier transform, but we are taking Fourier transform in very short duration. The assumption was this behind the STFT, that your signal will be stationary in very short duration, because whatever is changing or random phenomena is occur, kahin na kahin to wo stationary hoga. So if we got that limit where it is stationary, so we will model that duration by using our fixed basis, that is the e to the power minus j omega t. So previously, what is happening inside the Fourier transform? We were just multiplying with e to the power minus j omega t for the entire duration. In STFT, we are multiplying first our signal with short duration window. So here basis is changed. How basis is changed? We have a window that will take the sample of your entire time duration signal. Suppose your signal having a duration of 100 millisecond. So you just take the window of 1 millisecond and then multiply with e to the power minus j omega t. So in STFT, the basis is window w then e to the power minus j omega t. So that window will take the sample of very short duration, because we are assuming in this short duration our signal will be seems like stationary. So that's why we are taking the Fourier transform in that duration. But again, in each duration, your frequency is constant. Your frequency, that is e to the power minus j omega t, that basis is not changing. What you did, you just simply taking the Fourier transform in short duration, but you are not changing the basis. Still, it is same. You are not changing its frequency. Still, it is omega. So we need a more powerful basis, which oscillations or variations can be changed in different durations. So that is done by the wavelet transform. In wavelet transform, we have a more powerful basis with power of dilation and shifting. You can just expand or contract those basis function. So you can change their characteristics. While in Fourier transform simple FT and say or STFT, we cannot change the nature of that basis function. But in wavelet transform, using the dilation and also the localization by using the shifting property. So this thing is available inside the wavelet transform. So for a long decade, people have used this wavelet transform for analyzing non-stationary signals because they have a more powerful basis. And you can adapt those bases, you can change their properties, you can change their oscillatory behavior accordance with your signal. But still, that wavelet transform suffers a problem of fixed or rigid wavelet frames. So sometimes those frames are not able to extract the periodic impulses. Like suppose, if someone is suffering from seizure, so when the seizure attack came, at that time the brain signals show the impulses, or like some kind of apnea problem, sleep apnea problem. So during the problem or some kind of heart failure, in that condition we will see the sudden spike in that EEG or ECG. So those sudden spike are not able to represent by using wavelet transform. People also try to represent, but what they found, they are requiring hundred of wavelet frames for representation of that. If you use the large number of basis function, that will directly affect the complexity of your signal processing method. क्योंकि आप ज़्यादा basis use करोगे, then you have to implement in the MATLAB, then you will require some more time, and at the last you have to implement your algorithm on some hardware. So it will be computationally as well as hardware complexity, both will be there if you are using the more basis. So then the more powerful method is came. That means again we are giving more control or more power to our basis function, that is given for in terms of tunable Q wavelet transform, that you can tune your basis function with any kind of change like periodic impulses or any kind of oscillatory behavior. So you have a more parameter. Previously you have just only 2 parameters. Right now you have a 4 parameters in case of GQWT. So those 4 parameters can control more robustly the behavior of basis. From the beginning we are just controlling our basis function. Our only aim is to provide more power of our basis function. So on the basis of that, our signal processing method will get the advantages. So in TQWT, people have introduced 4 parameters for controlling the basis functions, and those 4 parameters robustly control the basis and also represent the non-stationary signal with all kind of variation and like sudden changes or transient changes. But still in TQWT, there are some limitations. Like we cannot use the arbitrary sampling rate, because if we want to process a signal on some kind of system like a multi-rate system, so we have to process our signal on different sampling rate or arbitrary sampling rate, and that thing is overcome inside the flexible analytic wavelet transform, because they have used the analytic basis and we can select any value of dilation factor and translation factor that was not possible in case of TQWT. So, motivation for introducing the adaptive signal processing method. First of all the methods requires a manually parameter selection. Like in case of TQWT, there is a parameter, or there in FAWT, there is also again 4 to 5 parameters. So you have to select those parameters manually, or we can say the empirically. Empirically means that means we are putting different values of the parameters, and each time we are just visualizing the reconstruction error or the value of reconstruction error, and when the reconstruction error is minimum, and we are continuing with those parameters, because if the reconstruction error is less, that means we are getting the good representation. So that empirical process will takes the time. You have to do the lot of testing manually. So that is one limitation of this TQWT and FAWT. And if suppose we are analyzing a particular problem in field of brain signal classification or heart signal classification or speech signal, so there is a data set, there are a lot of signals. If suppose there is a two class problem, so there is a large number of signal in both the classes. So what is the problem with these TQWT and FAWT? Once you select the parameters for few signals, then it will never retune for remaining non-stationary signals, because we initially told that each signal is generating with some random phenomena. So how we can fix our parameter? Our parameter should change for each input signal. So that is not available with this TQWT and FAWT. Once we fix the parameter, then it will remain fixed for entire set of EEG, ECG, speech, whatever, or any fault or seismic. So we need arbitrary, we need a each time selection or retuning of parameters for each input signal. So, and also we can say that once we fix the parameter, then our basis functions are priorly defined, because what exactly effect of selection of parameters, that will basically control your basis function. And once you keep them constant, so you define the prior defined basis function. And what is the problem, that if something is random or non-stationary, and again you are going to represent that thing by using some predefined thing or priorly defined thing, so that will not be a good approach. So that is again a problem. So that's why we need some kind of adaptive tuning of parameters or adaptive selection of basis function for each signal, not just for a set of EEG signal or set of ECG signal or set of non-stationary signal. We need a adaptive basis for each individual signal. This is our aim. So with the same, I suggested adaptive Hermit this decomposition will use the adaptive basis, and parameters are tuned for each input EEG signal, and the basis function inside this decomposition is directly synchronized with the analyzed signal. So again, what will be the basis function? What will be the basis function? Just wait. So what will be the basis function inside this decomposition? So in this decomposition, in this adaptive Hermit decomposition, I have used Hermit functions are Hermit functions are used as a basis function. And what is Hermit functions? Hermit functions are basically Gaussian weight functions, and these can be defined using the Hermit polynomials that we will see later. And in the beginning, I told you, if we are using the basis function for simple Fourier series or Fourier transform or anything, for any technique, that basis should be form the orthogonal set or orthonormal set. So these basis function, Hermit functions, forms the orthogonal set for finite energy signals, and we know that all practical signals are finite energy signals. Okay, so that's why they form an orthogonal set. So that's why they set up a completeness to represent any function or signal. So let's see the behavior of this Hermit functions and their mathematical representation. This is the mathematical representation of Hermit functions. So you can see it consists some Gaussian kind of term, and this HK is basically Hermit polynomials. So what we basically did, what I basically did inside the Hermit functions, there is a simple Gaussian weight functions, but it is controlled by using the Hermit polynomials. And if we see the visualization of these Hermit functions or signal, so what I have observed, it will depends their oscillation and their variation will depends on two factor. One is dilation factor and another is order. Here K is the order and P is the dilation factor. So when I put the order K equals to 20, this is the variation, and when I put the order K equals to 30. So what is the effect of order? If I increasing the order, then I will see the more oscillatory behavior. And what is the effect of dilation factor? Initially, I put the P equals to 50, or here I put the P equals to 100. So it's simply doing the expansion or contraction. If I reduce the dilation factor, it will do the contraction, and it will I will select the higher dilation factor, it will do the expansion, but it will not change the oscillatory behavior. Still it is same. So we can say it is like controlling the frequency. So number of cycles will remain fixed. So what I have observed inside this Hermit function, this basis function is directly controlled by their order and dilation factor. If we want to represent any non-stationary signal in terms of these two, in terms of these basis function or Hermit functions, what we have to control? We have to control simply order and dilation factor according with that input signal. So right now I have explored this adaptive Hermit decomposition, suggested this adaptive Hermit decomposition for EEG signal, that is also a non-stationary signal. You can apply for any kind of non-stationary signal. So as we have already discussed that this Hermit functions forms the orthogonal set or orthonormal set. So that's why we can represent an EEG signal in terms of this. Okay, so this Fk is basically a Hermit functions, and with some order K and dilation factor P, and this Ck is coefficient. And of course, whether you use any kind of signal processing method, कोई सी भी method आप use करें, there will be some reconstruction error. You will not get the zero reconstruction error. You will not get the ideal signal. So there is some error. Okay, so that error is represented by En. So this term is represented by some kind of approximated signal. Okay, so we are going to represent our signal in terms of some basis function with coefficient, and here K is the capital K is the number of basis function. Please pay attention, where a small k is the order of Hermit functions and K is the number of basis function, or you can say the number of decomposition level. Okay, so this is the this section is basically the approximated signal. So this is the approximated signal and this is the original signal. So there will be some reconstruction error. So we have find out the reconstruction error or mean square error between original signal and approximated signal. And our aim is to minimize this error, and minimize this error not for a single signal, for each input signal. And previously, what people are trying to do, they are just doing simply empirically. So right now, I have just explored some evolutionary techniques or optimization algorithms. So they will select these parameter with minimization of reconstruction error or adaptively for each input signal. There's no need to select the empirically. For each signal, what we have to do, we have to just supply that signal, and that evolutionary techniques or optimization algorithm will automatically tune the Hermit functions parameters like order and dilation factor. And the idea and the way they will select the aim of those optimization algorithm, try to minimize the reconstruction, and there where they will find the global minima or minimum value of reconstruction error, they will tune the decomposition parameter. Okay, so I have explored three optimization algorithm: genetic and particle and artificial bee colony. And this is the overall block diagram of proposed decomposition. As I told you, I have suggested this decomposition for non-stationary signal. So this EEG signal given as input. Okay, so this EEG signal given as input, so it will be decomposed in terms of basis functions. Now, here is the main role of evolutionary techniques, that they have to select the decomposition parameters, that means number of decomposition level and dilation factor. And remember, if you select the number of decomposition label, it automatically selects the order of the Hermit functions. So suppose in the beginning you have to give some initial guess to your optimization algorithm. So this initially there will be some value that will be provided by you, and this EEG signal will be decomposed in terms of some Hermit functions, that is HF, and there is a weighting coefficient also to control the error more robustly, that is called as Hermit coefficient. And once we decompose a signal, then we will get the approximated signal. Please, this thing is representing in terms of approximated signal. Okay, so once you decompose the signal, once you select the parameters, then your original signal will be decomposed in terms of Hermit functions. When you sum them, all of those Hermit functions, you will get the approximated signal. And what is our aim? Our aim is to reduce the reconstruction error. So you have to find out the reconstruction error between your approximated one and original one. So this is the original signal, and this is the approximated signal. So we have formulated the objective function, that is simply mean square error. Okay, so that optimization algorithm is will again check whether we are getting the global minima. If it is not a global minima, then it will try to find new solutions of that decomposition parameters. So this thing will go again and again and again and again. And once that evolutionary algorithm is not able to minimize the reconstruction error, then at that time, whatever is the parameter, that will be selected as the decomposition parameter. So once the decomposition parameters are fixed, you will get decomposed signal in terms of Hermit functions. And using those Hermit functions, we will estimate the Hermit coefficient, and that Hermit coefficient are used for feature extraction. So there is one more thing that I forget to mention over here. The problem that I have solved using adaptive Hermit decomposition, that is a sleep apnea detection using EEG signal. My aim to detect sleep apnea, or simple we can say the classify the apnea and control EEG signal using the adaptive Hermit decomposition and some machine learning algorithm. Okay, so it is basically a two-class problem. And sleep apnea, it is a kind of snoring problem. And due to this, there are a lot of cardiological disorders and brain disorders. This sleep apnea is responsible for these all kind of disorders. So this detection of the sleep apnea in early stage will help people to go in severe cardiological disorder condition or any brain disorder condition. So this is the aim of this sleep apnea detection. Okay, so once we decompose the signal, we will get the Hermit functions, and using those Hermit functions, we will extract some features in terms of Hermit coefficient, and those features are tested on extreme learning machine. Here I not did any contribution. My contribution is simply in the signal processing part, that is the adaptive Hermit decomposition, and that is simple ELM classifier, that is normally that we have used, and then I just evaluate the some performance parameter and compare with existing methods. So first of all, now come to our decomposition, that is adaptive decomposition. We have to test, as I told in the beginning, we have to test on all EEG signals. There is a 950 EEG, apnea EEG signals, as this is the two class problem, apnea class and control. Control, that means normal. There is a no apnea problem. Okay. So control means there is a normal EEG signal or without apnea problem. Okay. So in apnea class, there were 950 EEG signals, and in case of control class or normal EEG class, there is a 1150 or 1180 around signals. So what I did, I compute the reconstruction error for all the signals and just plotted their histogram. And what I have observed, the most of the signals, you can see something around 900, something around 1100. For most of the signals, the reconstruction error is lying in lower bin of that histogram. Lower bin, that means closer to the zero. The reconstruction error for most of the EEG signal or non-stationary EEG signal or non-stationary signals. Because why I am focusing on non-stationary, because you can apply on any kind of non-stationary signals. Speech के लिए, आप heart के लिए, heart signals sometimes called as quasi-stationary. Why we call them quasi-stationary? Because there is a repetition of PQRS. Okay, so or for any kind of signals you can apply this. So what I have observed the reconstruction error for most of the EEG signals, whether it is the apnea or control, lying in the lower bin, that is closer to the zero. So because if reconstruction error is not zero, not closer to the zero, then we will not claim that our proposed decomposition or good or giving the accurate result. So we have to test, because when we are not doing both part, decomposition is simply analysis part and synthesis is done in terms of reconstruction part. So we have to do the both thing, analysis as well as synthesis. Okay, so this reconstruction error is almost or closer to the zero. It is not exactly zero. It is in some range like 10 to the power minus 4 or 5 or 6. So but this is acceptable. That's why we can say that okay, the proposed decomposition is able to represent the non-stationary signals. So once we have verified our decomposition, then this decomposition or the features based on this decomposition are tested for detection of sleep apnea. So this is just a statistical analysis of features, whether we are able to extract the relevant change in apnea and control properly or not. So what we have observed that the probabilistic value, this is just a result of Korsakoff-Wallis test. This is simple statistical test. We just used to discriminate two classes, and the hypothesis is that if your probabilistic value, that is p value, is a 0.05, so it simply indicate that only 5% of populations are same in your classes and 95% populations are different. So what is the acceptable value? That should be less than 0.05. But right now you can see we are getting around something 10 to the power minus 30 or very smaller value, value less than the 0.005. So that population are matching in both the classes is negligible. So this conclude that the proposed features are able to discriminate apnea and control classes accurately. So once the statistical significance of suggested features is ensured, then these features are tested on extreme learning machine, and this is the result of extreme learning machine classifier. And this is given in terms of confusion matrix. So you can say the detection rate given on the diagonal for apnea and control. So it is something near around 99. And the performance of ELM classifier is depends on the number of hidden neurons. So I have tested with different number of hidden neurons to explore which one is the best. So what I have observed, for 120 hidden neurons, we are getting the best performance or best confusion matrix, and the performance in terms of sensitivity, specificity, accuracy, error, and F1 score. So for 120 hidden neurons, we are getting the best performance. And again, for checking the robustly the classification performance, we have plotted the receiver operating characteristic curve. So you can see for this for the input feature, the in the ELM classifier, extreme learning machine classifier, the true positive rate rises rapidly with a small change in the false positive rate, and the area under the curve is also closer to the 100%, that is the simply 99.5%. So this says that the ELM classifier for given input feature or given ASD based features having the ability to discriminate sleep apnea and control events accurately. And at the end, we have compared our results with the existing methods. So our proposed method provide the best performance measures as compared to the other existing methods. And I have also explored one more method, one more adaptive method, that is optimize a flexible analytic transform. In previous one, I have used the Hermit function as a basis function, and where I have selected the parameter using evolutionary algorithm. In this one also, this OFWT is basically overcome the limitation of FAWT that we have discussed, because what is happening inside the FAWT, that is we have discussed in the beginning. In FAWT, people are tuning the parameter empirically. So what I did, I just select the parameter of FAWT uh, by using some optimization algorithm, and those optimization algorithm will tune the parameters of FAWT for each input EEG signal. So first of all, understand what are the parameters of FAWT. This is the in each wavelet transform there is a similar pattern. There is a low pass filter, there is a high pass filter, there is a simple structure. आप जो बेसिक वेवलेट ट्रांसफॉर्म को भी देखेंगे, और उसके बाद है ना ड्यूअलिटी कॉम्प्लेक्स वेवलेट ट्रांसफॉर्म आया, और उसके बाद TQWT, FAWT, जितने भी है ना लेटेस्ट वेवलेट ट्रांसफॉर्म आए हैं, उनमें सिमिलर स्ट्रक्चर. Again, there will be a two channel, low pass, high pass, a detailed approximation, similar thing, pattern wahi hai na. So the frequency response of those low pass and high pass filters are defined like this. And so we can say that because right now these filters will define the basis function. What is exactly the aim of any signal processing method? We have to define the basis, and the entire thing will depend on the basis function. Okay, so these filters, low pass filter or high pass filter, will define your basis function, and these basis functions are depending on some parameters. And what are those parameters? Those are parameters are basically P1, P2, P3, and P4 and beta. Okay, so previously these parameters, these decomposition parameters, were selecting empirically, or we can say like manually. The situation is like this in FAWT. Once we have selected the parameter, that will remain fixed. Whatever signal you give at the input of FAWT, it will remain fixed. Those parameter will remain fixed. And what I did inside the OFAWT, again the similar thing that I have done in the ASD. I just estimated the reconstruction error and use some optimizer, and using that optimizer, I just try to minimize the reconstruction error. And once we get the minimum, same pattern that I did it with ASD, the same thing I did with OFAWT. And right now in this presentation, I not included the reconstruction error for FAWT and OFAWT. And what I have observed in case of FAWT, the reconstruction error in range of 10 to the power minus 10, and with OFAWT, the reconstruction error sorry, the reconstruction error is in the range of 10 to the power minus 16. So that means we are getting the better representation. So pattern is same. Simple optimization ka use kiya, and then those parameters are selected for minimizing the reconstruction error. Okay, and the problem that I have solved using this OFAWT is the sleep stage classification. My most of the work is on EEG signal classification, or basically the brain, biomedical signal classification. But these methods can also be explored for any non-stationary signal, speech, fault, vibration. People already use FAWT, explore FAWT in the mechanical domain for fault signal identification, or vibration signal identification, and also on speech signal. So this OFAWT can also explore for those domain. Okay. So what I did, I simply initially I have decomposed a signal, EEG signal, into some subbands, because जहाँ wavelet आया वहाँ subband आ जाता है. Simple the terminology, like we are dividing a signal into different frequency band that we will call as subbands, and using those subbands I have extracted four features, that is average amplitude change, clearance factor, intercollinear, simple square integral. And these features are tested on several machine algorithms. And what I have observed, the Bactry ensemble classifier is providing best results for sleep stage classification. And basically, the sleep stage classification is a multi-class classification problem. Okay, so the combination that will be possible, 2 class, 3 class, 4 class, 5 class, 6 classes, and these are basically the all the stages that a human being will go through in the whole night. Like AW means awake stage, S1, S2, S3, S4, or and rapid eye movement. So these stages are defined by some international standard, that is the RNK standard, RNK standard. And there is a significance for classification of these all the problems, 6 class. And in 5 class, what we did, uh, people have observed that S3 and S4 have a similar kind of behavior. S3 and S4 having the similar kind of behavior. So these can be commonly called slow wave sleep. And again, with S1 and S2 similar kind of pattern, that is shallow sleep. And again, S1 to S4, this non-rapid eye movement, that means during the sleep your eyes are not moving. What is the meaning of rapid eye movement? Your eyes are moving. Awake means you are not sleeping. And non-rapid eye movement, that means you are in the deep sleep, your eyes are not moving. And again, you can form a simple problem, awake or sleep. That is a 2 class classification problem, in which S1 to S4 भी आ जाएंगे and rapid eye movement भी आ जाएगा. Okay, so in this way we can form the different problems. And in classification problem, the first stage to ensure the statistical significance of your features. If your features are statistically significant, then you should test on the classification. If your features are not statistically significant, then you will not get the good performance. So it is basically a multi-class classification problem. So that's why I did the multi-comparison test or post-hoc analysis for the extracted features. As I have mentioned, there were four features. That is the average amplitude change, clearance factor, interquartile range, simple square integral. Simple square, just like some kind of energy proportion. Okay, so in that post hoc analysis, we will compare the distribution of features for different classes with respect to their mean rank. And this circle, this black circle and some distribution, black circle and distribution. This black circle is representing the mean rank. If this mean rank for different classes are overlapping, for example, like in this one, clearance factor, you can see there is a little bit overlapping for S4 and awake. So we will say that, oh, this features is providing poor discrimination. Okay. But for most of the feature, as you can see, the distribution of features with respect to their mean rank is not overlapping. You can see S1 and REM. S1 is not overlapping with all the classes. This S2 is not overlapping with all the classes, and same with S3 and same with S4 and awake. So what I have observed for my suggested features, there will be a negligible overlapping among different classes. So that ensures my statistical features or the features presented by OFAWT provided subbands are statistically significant. So now I can test these features for the classification performance evaluation. So I tested on Bacteria Ensemble classifier. You already aware of this. This classifier is present inside the MATLAB classifier learner app. Inside the MATLAB classifier learner app, there are different machine learning algorithms, and right now they have included the. I think last year or last before last year, they have included the optimized one also. In optimized one, again same thing. What I did, I in a ESD or a OFAWT, I use the optimization. So they have also added the optimization algorithm for selection of parameters of machine learning algorithms. So in that optimize the ensemble class, like optimize the ensemble classifier, what they did, because each machine learning algorithm, even deep learning also, they will depend on some kind of parameters. So again, problem is same, whether you have to select those parameter empirically or automatically. Automatically, there is a best way. You simply use optimization algorithm. So they simply added the optimization plus classification. Okay. So this is the confusion matrix for all the problems, classification problem. 6 stages, 5 stages, 4 stages, 3 stages, and 2 stages. And that diagonal element shows the detection rate in corresponding stages. So you can see the value for diagonal elements is quite high for all classification problems, for whether it is a 6 class or 5 class or 4 class or 3 class or 2 class. So this is a comparison with all existing methods for sleep stage classification. Okay. So right now I compared only with two standard, because these are the main problem. RK, that standard means it is a 6 class classification problem, and ASM means there is a 2 class classification problem, because in ASM two stages are combined. This is a, you can see in R and K standard there are 6 classes, no combining. All stages are just individually. Okay. In case of ASM, American standard, so two stage S3 and S4 combined, and they say like that. Okay, there is a negligible change in S3 and S4. So why we should not combine them? So in this American standard, they combine this S3 and S4, and they simply call them shallow wave sleep, and it become a 5 class classification problem. So these two are the major classification problem in the sleep stages. So you can see the comparison with all existing methods, and our proposed method is providing the highest value of accuracy, which simply says that the accurate classification of all the sleep stages, and kappa value is also higher, which simply shows that we are providing the stable classification performance as compared to the existing methods. So this is the all about the adaptive signal processing methods. And now come to the conclusion and future directions. So my aim is to simply introduce adaptive signal processing method that I did in terms of adapt. sorry, sorry. That I did in terms of adaptive hermetic composition and OFAWT, where parameters are selecting automatically. Where parameters are selecting automatically, there is no need of selection of manual parameter or empirical parameters. So what you have to do, you have to just input your signals. It will automatically select. So we can say that we are selecting the parameter for each input signal or each non-stationary signal. So we are providing adaptive basis. This is the main thing that we have required for a representation of non-stationary signals. Okay, so not to worry about the this non-stationary EG, you can mention any speech or any seismic or any kind of signals can be used for representation of these methods, because sorry, because EEG is one of the complex form of the signal. Even in ECG, there is some kind of repetition, and in speech signal also you will see some kind of envelope, and you will find that in that envelope it will be gradually its amplitude is starting, then it will start decreasing. Okay. So if this method is working on the EEG signal, then definitely it will work on other non-stationary signal also. And the proposed adaptive decomposition based features provide the better brain state classification performance as compared to the state of the art methods. And what is the future directions? Right now I have not checked the effect of artifacts. आप कोई सा भी सिग्नल रिकॉर्ड करें, चाहे स्पीच सिग्नल और ब्रेन सिग्नल, हार्ट सिग्नल, एनी टाइप ऑफ सिग्नल, seismic signal, fault, of course if you are recording in a surrounding there will be artifacts. अगर कहीं का आर्टिफैक्ट्स नहीं है तो पावर लाइन का तो आर्टिफैक्ट्स तो अवेलेबल ही है ना? सो देयर विल बी आर्टिफैक्ट्स. सो राइट नाउ आई नॉट टेस्टेड the effect of artifacts. And second thing is sampling frequency, because when we are recording a signal in a digitized way in terms of samples, so there should be some sampling frequency. So if suppose right now I just tested on 256 hertz sampling frequency, means 256 samples are taken in 1 second. So if we change the frequency, like up sampling or down sampling, lower sampling rate or higher sampling rate, then what will be the effect of this ASD or OFWT, whether they will provide the less error or not error, or higher error. So this is not tested. So this can be investigated. And proposed decomposition can explore in any domain that I have already told that, because if it is working on EEG, definitely it will work on other signals also. And right now I just explore Hermit functions as a basis function. So you can explore other basis. There are a lot of basis functions. There is one book that I have mentioned in the reference. So, and in mathematics, what you have to do, those who want to work in this domain, प्लीज जो मैथमेटिक्स की रेफरेंस जो बुक्स हैं जहां पर फंक्शंस डिफाइन है ना, so this hermit functions is also defined inside the some mathematics book. So you can explore different mathematical function, and you have to check first, you have to check whether they are, those functions are forming the orthogonal set or not. If they are forming orthogonal set, this is only the criteria for hermit for decomposition or signal representation method. So if they are forming the orthogonal set, then you can use them as a basis function. So you can explore new basis function for analyzing the non-stationary signals. So these are the references. Thank you. Any question? So in the chat box, there is no question. Any question from the side of participants?
Any
Professor,
question,
am I
please?
audible?
Yes, you are audible. Yes, you are audible. Yes, sir.
Yes. So this is the afternoon session, so no question.
Okay, no problem. So I think then we can wind it up for today.
Okay.
And then we will not meet tomorrow, right? Okay. So thank you so much, Dr. Sachin. So let's wind up and see you all tomorrow, right?
Thank you all of you. Yeah, and in WhatsApp group, we will share the all 3 session link. So you just fill the feedback form. Okay. Thank you all of you.
Yeah, sure.